All right, we've moved on from means to proportion. So here's our very first proportion. It'll be a confidence interval problem. This is 2013 question 2. It's from the international exam. A certain company makes 3 grades of components, A, B, and C, of a particular component. Historically, grade A have a 2% defective rate, grade B has a 5% defective rate, and grade C has a 10% defective rate. Since grade A components are less likely to be defective, the company can charge more money for those components than it can charge for grade B or C. Similarly, the company can charge more money for grade B than it can charge for grade C. Recently, the company found a batch of components in a warehouse that were known to be of the same grade. The grade was not labeled. To determine the grade A, B, or C, the company selected from that batch a random sample of 200 components, which contained 16 defective components. Construct and interpret a 95% confidence interval for the proportion of defective components. Well, first off, what is my defective? Well, I have a p hat of 16 over 200. So I have 16 defectives out of 200 that were sampled. And they want to construct a 95% confidence interval. So PO is the true population proportion of defects in the batch. And we're going to try to estimate that using our p hat. Random sample, they gave that to us. N is less than 10% of the population. Reasonable to assume that there are more than 2,000 electrical components in this batch. So NP hat equals 16. We have 16 defects, and N times Q hat, or this could be also written as 200 minus 16, is 184, and that's greater than 10. So the sample is large enough to use the normal approximation. It just needs to be greater than 10. So how do I go about doing this? Well, my formula is p hat plus or minus z star times, and we're going to cross this out at some point. But that's what we work with. Well, what is 16 over 200? 16 over 200 is 0.08. So we can go ahead and plug in 0.08 and 1 minus 0.08 over 200. And I need to get my z star. Well, all proportion tests are z statistics. So second vars, inverse norm, parenthesis 1 minus 0.95, close parenthesis, divided by 2. And we end up getting 1.96. And I'm going to go ahead and start plugging in my values. We're going to go ahead and run this test. It's stat test, one proportion, z interval. And I had 16 defectives out of a sample size of 200, 95% confidence interval. And I end up getting this 0.0424 is my lower bound, and that's my upper bound. So we are 95% confident the true population proportion of electrical defects lie within this interval. All right, so I don't know where it is. It could be as high as 10% or as low as 4%. So does the interval calculated in part A allow the company to clearly determine the grade of component that's produced? Well, we know that A equals 2%, B equals 5%, and C is 10%. Well, we know it's not A. We can eliminate A because A doesn't lie within the interval, but it could be either B or C. So we need to say that, hey, we know it's not A, but it could be either B or C, and we cannot make that determination. Okay? And that will take care of our first of the proportion problems.